This is from a project called COAST. It was multi-channel seismics offshore. What we're trying to do here is be an integrative, bring together GeoPRISMS, EarthScope, and the Cascadia Initiative, and show you some new data that was collected last summer. So this is part of, as I just said, Cascadia and EarthScope. We're going to be looking at marine, onshore, offshore, active source data. It was called the Coast Cruise in July of 2012. And we'll show you some preliminary data examples we're emphasizing. There's some contentious stuff here that we'll see that might have to do with velocity analysis being not what we'd hope it to be. And then some notional future work. You've all seen this before. This is the amphibious on the offshore there, and showing you all the instrumentation that we have collected and proposed over the next 2 years for this initiative. So COAST is the data I'm going to show you today, which is just north of where the Columbia River comes out on the northern edge of the Astoria Fan. Of course, if you follow that plate trajectory down, it ends up under Seattle where the ETSs are. So this would be important. These are the inputs to ETS. And also from a guy that likes to work deeper in the mantle, the amount of sediment and fluids going down in terms of the geochemistry of the arc, and also as an aficionado of the transition zone, maybe not here, but how much water could get down into the transition zone. You see other lines here, so there's some other data to the north and the south, some old lines. Of course, this new multi-channel data generally does better than what the Langseth is getting these days. Steve would argue, and I guess I'm arguing too, that the marine active source is a critical need here to understand basically in this forearc region with an underflowing plate, how the sediment deformation is being accommodated. And the first order question is how much sediment is actually going down the slot and making it down, and how that's interacting with the frictional properties as manifest by the episodic tremor slip events there. Okay. So always the why question, why here? Here's listed some of the bullet points for why here. Accessibility, close to major port, synergies, as always, and numerous targets here. So I think it's an obvious spot to do it. It's in the lower 48. Obviously, it's one of the focus sites, and we have Alaska and East Coast, and New Zealand is other ones. So it's our homeland, so to speak. A new paradigm for this program. Those of you that are aware with the ocean facilities programs, there hasn't been an EarthScope paradigm for sharing data. Okay, there was on the books, but de facto there wasn't. They've gone to an open access, open data policy now. And so that's a big change in what's traditionally been done in the past, much more EarthScope-like. And the hope is to somewhat rejuvenate the program in terms of multi-channel offshore seismic collection. The things that the Langseth garners for us is in the Coast project, they collected 1,100 kilometers of MCS data, bathymetry, gravity. The Sparker data didn't work. There was a mechanical failure there. They only used one streamer. Cost more energy to pull all 4 streamers. So it was a 2-dimensional profile and a standard gun array. And they tried 2 different depths, 8 and 15 meters, to try to tune up the source signatures, and particularly to get to the lower frequencies. There also was a piggyback by Ann Trehue and Jeff Abers that apparently recorded at the far offsets. I think Jeff told me 140 kilometers. They were getting the gun data on shore, so that's good. The operational goals of this project were the nominal ones, of course. Where's the plate boundary, down dip variations, nature of the plate boundary, the big one again being subducted sediments, and how much are making it down the slot and getting under Seattle, for instance, or Portland. That, of course, would co-vary with the porosities and fluid pressures and interpretation of our seismic images, for instance, from CAFE, and trying to understand the physical properties that our seismic images reveal. And also, of course, at the end here, we're going to have a next big thing, how this current data set can be used to leverage and extend and propose a larger scale project. As I said, the E&O goals, the raw data is listed there, and the migrated stacks is down at Austin, and you can click on that right now as you're seated and recover that data, and that truly is a new paradigm for this program. Also, open participation. All bunks were full on the boat, and anyone can go pretty much. So call up Mom. Mom, she might want to take a boat trip. So here's just an example of the open access for the coast data. This is the migrated stacks at Austin. This is the raw data that's at Lamont Doherty. This is the open participants being very open with their smiles. And there, you can see Steve in the upper left there, and Harold Tobin, and so on and so forth, and a lot of smiling graduate students. This is their list of their names, broke down into 20 participants, 14 institutions, and 13 so-called newbies. Fun was had by all, I'm told by Steve. So these are the track lines right here. So again, this was a 2D streamer format to collect the data. And steaming basically on the outer shelf, they had to stay out of the shallow water because of biologic issues. Of course, the free air gravity is, well, free, more or less, when you're on the boat and paying for it. So this is just an example, and this will be important to understanding and the physical properties from the seismic images. Magnetic data too, of course. This is probably the most sensate multi-beam bathymetry data, and as you can see here, we have right here is where we're diving under the sedimentary prism, and we have these compressional structures in here. So you can see geology in action in this kind of environment, which is cool. Backscatter intensity data, basically to assess the albedo of the surface there, and of course properties can be gleaned from that, kind of like cratering statistics in my mind in terms of the youth of the surface and matters such as that. So now I'm going to give you a preliminary tour of the findings. I think the emphasis here, especially since I didn't process this data, is preliminary. And I do have some caveats here and a provocative so-called paradox. So emphasis on preliminary. So you can see what I'm going to show you there in the 4 bullets. Let you read that for a second. Okay. So here you can see on your, I'm dyslexic, on your left, you can see the bathymetry, and then we have 2 blow-up boxes there to your right. And in the upper one, you can clearly see some landslides coming off that first compressional ridge structure there, where the plate's diving down there. And you can see down here, for instance, again, there's a big slope failure in here, and run out and scour into here, down in here. So, you know, you could imagine this could relate to the long-term evolution of the system, and also maybe to the magnitude 9 that hit this region in 1700 there, and relate those. That, of course, we need to get some dating down there to make more of that. Active normal faults here. So if you look right here, you see an offset in the bathymetry there. And moving onwards, if you look into the subsurface under that scarp there, you can see right here is what we're looking at, and you can see a generally listric fault going downwards with gross stratigraphy in the downdrop part of the half graben there. So geology in action. Another example of, in this case, an active normal fault. You can trace it from here. There's a graben here, and we can trace it down here. This is a time migration coming down and then flattening out right in here. So a nice example of a beautiful listric fault. These could relate somewhat to tsunami hazards with big slump causing a water displacement and hence a wave. A funny thing in this data set with respect to critical taper theory on the evolution of these wedges is the structures here are landward vergent. So I point examples in here, and here. And that's atypical for these kind of margins, and I'll come back to that a little later. Again, to emphasize these landward dipping vergent structures, the land's over here. This is east, and this is west right here. You can see it's coming up onto the shelf here. We'll come back to that. So a primary target, of course, is the top of the oceanic crust here, which in the deeper parts offshore, you can see the top right here. And then it goes away, and we have what look like diffraction smiles to me over and in here, but maybe right along in here is the top of the oceanic crust going under the prism there. The question would be, the image quality is invariant across the gathers in terms of the fold. So probably some reals happen in here in terms of the impedance structure on top of the oceanic crust, and you can think of many reasons for that. Same idea. This is a time migration right here. And of course, this is a little goofy in the time domain. The way it's kind of looks like it's coming up, it needs to be put in the depth domain. And again, these landward verging features here that come up and cause these little topographic highs here coming down. The faults, I must admit, don't look that great on this one, but I'll show you another one. And again, to emphasize this landward weakening, let me see how this looks to you. Okay, coming in here, this again would be the top of the oceanic crust, and it's diminishing as we move onshore again. So, and they don't believe that, again, is an acquisition issue. Going a little farther south with some older data, this is an interpretational drawing. This is off Oregon. Here, and you can see these fault structures coming down and rooting into what they're calling a décollement right along in here. And then the top of the oceanic crust is a little bit underneath it. So this section right in here, you see, okay, is a little bit of the sedimentary package that's been being underflowed under the continental margin, and hence would be important to understanding the frictional evolution of the interface under the Willamette Valley in this case here. Now going back to the coast, data acquisition section here. I'm going to move on from this one to this one here. And what you would like to note right here is on the orange line, we have this fault coming down from the surface topographic bump here. And it's going all the way down to what they're interpreting as the top of the oceanic crust there and rooting right on top of it. So if you take that at face value at this sample spot, this is just one spot along the margin, in this case it would appear with that rooting down to the top of the oceanic crust that an inference could be that no sediments are being dragged down at this point in space and time on this section. Okay, this one's just for context again. Show you the top of the oceanic crust is down here. Now, this is where it gets a little interesting. So this is a sedimentary prism here with its stratigraphy. And we have, this would be the top of the oceanic crust, since it's the highest amplitude. But you can see this is not a flat surface. Okay? And the question is, if you interpret this as is, and I'll give you the alternate here, then over in here we must be facing increasing frictional stuff. Those stresses are being propagated up, and we're causing faulting at the top of the oceanic crust there to create that structure. If you don't like that one, and again I emphasize the word preliminary, these could just be artificial apparent push-up pull-downs from inaccurate velocity migrations into the depth domain here. So stay tuned on this one. That would be provocative. We'll see what comes out of this structure here. So going back to the landward vergence stuff, which you can see down here, the faults are all going up dip. They're all sloping towards the east, which is where the land is there. And the requirements for landward vergence are low basal shear stress and landward dipping décollement. We have that, of course, and a strong wedge relative to the weaker décollement frictional properties there. So if you can satisfy those three, then you can explain these landward vergences in that sense. And that's telling us something, most importantly for the science on this project, is low basal shear stress on the megathrust down there. And so they're proposing that, given what I showed you previously with the topography on the top of the oceanic crust. You could pose this as a paradox question, whatever that means. How can the low basal shear stress be achieved if the décollement is not in the sediments and we're actually deforming the ocean crust, as I showed you in this picture right there? Okay? Stay tuned on that one. What next? So this is, I guess, the next big thing, to integrate the Cascadia Initiative, GeoPRISMS, and EarthScope. They have these current data sets I'm showing you right here. Sohn was collected by the Germans. Oregon collected the 89 data set, and the coast is what I just showed you images from. And there's some industry data in there that you can't see very well. So, of course, we have MUCHA, which you saw earlier with the magnetotelluric survey. Of course, the Cascadia Initiative is running with the OBS data, and that's being analyzed. And what they want to do, of course, surprise, surprise, is cover the whole margin, keep stepping southward towards the Mendocino triple junction they believe would be wisest and not going north. One more slide. So the rationale for this project would be, as you can read here, basically to coordinate with all the other data acquisition activities. They would need for the survey plan down here a single 40-day leg of the Langsath to collect data, and a second ship for the OBS deployment. And so as you can see along the margin here, they'd like to extend the coast data all the way down towards Mendocino to characterize and look at the three-dimensionality of the structures. And of course we have the plate vectors modulating, the configuration of the margin, the sedimentary inputs. Obviously the Astoria fan is big to the dispersal off there, and figure out how the sediments are going down and how that would relate to the deeper structures in the ARC and in the ETS observations. Okay, thank you. Yep.